Okay, so carrying over from last lecture. So what we did in the last lecture was basically we developed relationships between the throat condition, the reservoir or stagnant conditions, right, in a flow field, right, in a flow field. Now let us see if we can do something specifically for a normal shock. Okay. So let us go ahead and do that and see if answer some questions in terms of how basically a normal shock is formed. Now say this is a so again this is my a normal shock. Okay, this is region 1 and 2. Okay. Now I'll just rewrite the basic governing equations. Okay. So this is the continuity equation. This is the conservation of momentum equation. Right, and this is the adiabatic energy equation. Okay. Now, one thing I'd like you to be careful is the similarity of this this relationship, this equation with the Bernoulli's equation. It looks very similar, but it is very different. So be careful when you write this equation or when you use this. Okay, so the flow field in a normal shock is going to be governed by our three relationships like this. Okay, so let's develop a few relationships and see if we can have a little more information. Okay, now we'll also use these relationships in tandem here. So which means that our gas is calorically perfect. Okay, now one of the questions to ask, especially in a shock wave, like we have done before. Number one is what exactly is a shock wave. So I have tried to give examples for that or to explain that in a more crude way. Now one question to ask is that when exactly is a shock wave formed? Is it that is it that you have a very high supersonic flow now that really slows down here to subsonic, and then we have a shock wave? Could it also be that I actually have a subsonic flow and it speeds up to very high speed, supersonic flow, and then we have a shock wave, right? Or is it that we have a very, very high Mach number flow and slightly less Mach number flow, right? Both are supersonic, by the way, and we then have a shock wave, and so on and so forth, and so on and so forth. Or if we have a sonic flow and that kind of sonic flow, and then that causes what happens here. Does that cause a shock wave? Now what is it that is in our equations or in our relationships that will tell us this? Okay, one of the questions to ask is that. So let us see if we can use our governing equations to find some of these answers. Okay. So essentially what we are looking for is a relationship between the flow properties and the incoming Mach number, right. So, how the flow properties change across a shock wave depending on the incoming speed of the flow, right. That is what we are looking for. So, let us see if we can get some of those answers from our governing equations. So, let us do this over here. Let us divide the second equation by the first. Okay. So, what we will do is take the second equation, divided by the first, and what we get is this. Right, we get this, or is this, right. Now, we can also write, let us introduce the speed of sound in here. So, now we know that A is equal to rho. Okay. So, what we can write over here, right. So, therefore, the relationship becomes okay. So, we have a relationship like this, right. So, we basically combine the momentum equation and the continuity equation, introduce the speed of the sound, and this is what we get. Okay. All right. Now, using the energy equation, right, using the energy equation over here, what do we get? Let us see, let us use that. Okay. So, okay. So, we know that this can be written as okay. And from here again we can introduce this, because the speed of sound is, right, this is true as well. So, if I do that, so therefore, what I get from here is also okay. So, what essentially I get from here is this, okay, is equal to okay. Now, let us do a thing over here. Okay. Let us introduce a region which we will denote by the properties at which we will denote by a subscript star. Okay. Let us just try to understand what we are trying to do over here. Now, say I have in this region which is before the normal shock. So, let us say we have a supersonic flow. Okay. We have, say, a supersonic flow. So, this is the actual Mach number. So, we have a speed, this is the actual flow speed, flow velocity, and this is the actual speed of sound, right. So, this is a supersonic flow coming in over here. Now, let us slow this down, right. Let us slow this down such that it reaches a Mach number 1. It reaches a sonic condition Mach number 1. The corresponding speed of sound here is a star. Okay. Now, this is an imaginary case. So, we just saying that we have a supersonic flow and we are going to slow this down, we are going to slow this down adiabatically and bring it down to a sonic condition which is m star, which is sonic condition which is m star is 1, and the corresponding speed of sound is a star, right. So, which means that the velocity at this point then is a star as well, isn't it? Okay. So, if I had to do that, now we could do similarly another we could also do this in this way, that say I have a speed of sound, a speed of the flow which is subsonic. So, say in this region or in this region itself. So, instead of the speed being supersonic, say this is subsonic. Okay. So, say we have okay. So, say we are coming in. So, say we are coming in with a speed which is subsonic, and the corresponding velocity and speed of sound are u and a, right. It could be either supersonic or subsonic. In this case, we will again reach this sonic point by speeding up the flow. So, we speed up the flow so that it becomes sonic, okay, and the corresponding Mach number here is a star. Okay. And we will see the usefulness of this as we introduce it into our equation. So, it could be either, right. So, what we are not assuming here, what we are not able to assume here is what exactly is the incoming Mach number, right, or the speed of the flow which will actually cause a shock wave, right. We just assuming that we do not know that, right. We will do all these studies and then try to get an answer for that. Okay. So, coming back to our equation here, if we do have that, okay, if we introduce the star region over here, instead of this taking the second region as the sonic region, so what we will have there is that this becomes a star, and at that point this is also equal to a star, right. If we have that, then what we will get, this equation therefore then becomes right. So, what this relationship is basically telling me that if at a particular zone, the actual flow of the actual velocity of the flow is u, the actual speed of sound is a, then let us get a region where which is sonic, the corresponding flow velocity, the speed of sound there is a star and the Mach number there is 1, right. Then this is the relationship, and nothing here is actually telling us whether I am supersonic or whether the velocity there is supersonic or subsonic. It could be anything from this region, because if it is supersonic I can slow it down to the sonic zone, and if it is subsonic we can speed it up to the sonic zone. Okay. So, nothing here is actually giving me any clues as to the incoming Mach number. Okay. So, if I do this, right, now let us do that. So, therefore, what we will do is write this for these two zones, right, say 1 or 2 zones, and what we will get is this. If I write it out, okay. so okay. So, this is what we get by bringing in two regions over here, A1 and A2, right. So, either of this A1, so A1 is in region 1, okay, and A2 is in region 2, okay, and nothing here is telling me that the region 1 has supersonic flow and region 2 has subsonic flow or vice versa. Okay. We are just saying that the flow reaches, we are able to slow it down or speed it up to the sonic zone. Okay. So, if I do this, so what we will do is use these two in the relationship over here. If you see, this is the relationship which we had developed first, which I denoted by A. So, what we will do is use these two expressions. So, we will input in A and divide that by U2 by U1, right. We use these expressions in the equation A and divide that, and what we get is this. What we get from there is this. Right. So, what this is telling us is the relationship between the velocities in region 1 and 2 with respect to the sonic zone. Okay. So, then that also I can write as right. So, all I am doing is now I am basically dividing by the speed of sound in the imaginary sonic zone. Okay. If I do that, then what I get is, what this gives us is m1 star m2 star is equal to 1, right. So, now this relationship, essentially this relationship is the Prandtl-Meyer equation. Okay, this it is credited to Prandtl-Meyer. Okay. So, then this is the relationship that we get. Now, let us see if we can make certain inferences from here. Okay. Now, we will write it like this, and also, so I can also write it in this form. Now, so let us write that over here. Okay. So, then what I will write is okay, and I am going to call this as the relationship B. Now, if you see over here, so you can see from this relationship as well. So, what we can do is divide this by u square. Right. If I divide this by u square, what I get is this. So, basically I am dividing this by u square. So, what I get is this. Right, or I can write this as basically, or I can write this as right. So, I can write this as okay. So, see if you agree with me on this one. Okay. So, all I am trying to write this just in terms of, because this gives us a field for the Mach number. So, then I can actually write this equation as right. So, this is the actual Mach number, right. So, this is the actual flow velocity and this is the actual speed of sound, okay. And this is the flow velocity with the sonic zone speed of sound. So, this is the m star, okay. So, if I write this, okay. So, then from there I can basically write that in, I will write it in this form. So, m square is equal to okay. So, what now we are able to do is basically look at get a relationship between m1 star and m2 star, right, and the actual Mach number and the sonic zone Mach number. So, we have got these two relationships and now let us study from here what are the mathematical characteristics from here, okay, and see if we can infer something more in from these relationships. Okay. Now, although we have basically said that m star is the m star out here is the sonic zone, m star is equal to 1, right. Now, just for a wee bit, let us just forget whatever we discussed so far and treat this just as a mathematical entity, right. If you give this relationship to somebody who has not heard the discussion what we just had before, then this is just a number to him, okay. So, if I am just looking at this from the mathematical point of view, let us try and decipher what we can from this relationship, okay, and we will go back to these physical implications after that. Okay. So, if I do that, now let us look at this relationship over here from C, okay. Now, if m star is equal to 1, what does this tell us over here? If m star is equal to 1, what is the n? Okay. So, just try putting m star is equal to 1 over here. So, if I put that, what do I get? Okay. M is also 1. So, if m star is sonic, m is also sonic. Okay. Now, let us say m star is supersonic, then what do we get over here? Okay. I think the best way to do that is just take a put a value for m star, say 2 out here, and then see what will you get for Mach, the Mach m, right. So, let me just say that Mach in this case is also supersonic, and similarly if it is subsonic, best thing to do is just put an actual value. So, take gamma is equal to 1.4 say, which is the standard value for air, and put an actual value of m star. If it is subsonic, say put it at say 0.5 or something, and then see what you get for the Mach number, right. So, verify whatever I am writing over here. Okay. I am saying that if it is 1. This you can see right now itself, m star is 1. Now, verify this for yourself if I am correct. So, if it is supersonic, then m is also supersonic. If it is subsonic, this is also subsonic. So, this is what we understand from C. Now, there is furthermore. Now, if say in this case, another case is that m tends to infinity. If m tends to infinity, then what do we get for m star? Okay. What do we get for m star? Well, just try to put it over here, just put m star. So, what we actually get is that this denominator basically tends to 0, is not it? So, what we get if m star tends to infinity, what we get is isn't it, right? If that is true, then basically from here m star tends to okay. So, this is what we get from here. So, essentially, this is the inferences from the relationship between the actual Mach number and the sonic zone Mach number, or the okay. Let's this is typically in some of the books this is called as characteristic Mach number. So, let me say the characteristic Mach number. So, the actual Mach number and the characteristic Mach number. So, this is the inferences from this relationship. Okay. So, what this is telling us, what is this exactly telling us? The actual Mach number is tending to infinity. It is infinitely large, and then the characteristic Mach number tends to a finite value. Okay. So, whether we are if we have an exceedingly very large Mach number, okay. Now, this m star has a finite value depending on the type of gas, because it depends on the gamma, right. It is not tending to infinity, or it is not becoming exceedingly small. Okay. So, now whether in those conditions also we will have a shock wave is something that we still need to see. So, there is only a finite value of m, a characteristic Mach number, that we will reach even if I increase my incoming Mach number to infinity, even if I make it infinitely large. So, that is what I am understanding from here. Okay. Now, let us use this information here, the between m star and m, and try to see get an inferences for m1 and m2. Okay. Now, if I do that, so now inferring from here, now say if m1 star is greater than 1, right. If m1 star is greater than 1, then what we get from m2, which means that the inference from here is that m2 star is less than 1, right. So, that we can infer from B, but what can we infer from this again? If m1 star is supersonic, if it is supersonic, which means the corresponding m1 is also supersonic, right, which means the corresponding m1 is also supersonic, right. Now, m2 star is subsonic, which means the star value is subsonic, therefore, the corresponding actual value is also subsonic, which means m2 is subsonic, right. So, therefore, what we are trying to say here is that if m1 is supersonic, then m2 is subsonic. Okay. All right. Another possibility is that, so this is say case 1. Now, case 2 is that m1 star is less than 1. m1 star is subsonic. So, which means that m2 star is supersonic, isn't it? So, m2 star is supersonic. Okay. Now, m1 star is subsonic, which means the characteristic Mach number is subsonic, the corresponding actual Mach number is also subsonic. So, M1 is also subsonic, right, and M2 star is supersonic, the characteristic Mach number is supersonic. So, therefore, the corresponding Mach number is also supersonic. Right. So, here M2 is also supersonic. Okay. So, what we understand from here is that if the incoming Mach number is supersonic, then across the shock wave it will become subsonic. If the incoming Mach number is subsonic, across the shock wave it will become supersonic. Okay. Now, we still need to answer the question that, so they basically therefore both these possibilities exist, right, both these possibilities exist. So, we will see if that is a valid assumption, if that is valid, or maybe not, maybe only one is possible. Okay, nothing as so far that we have studied or talked about gives us that clue. Okay. All right. So, now if we do that, let us see. So, we develop this relationship over here. Okay. Now, we wrote that in terms of m square. Let us write that in terms of say m star square. Okay. So, what we get from there is this. So, m star square is basically okay. I am just writing this relationship in terms of m star. Okay. Instead of m square, I am just writing m square. It is just rewriting the equation, nothing new over here. So, then this is the characteristic Mach number. Okay. Now, what I will do is here we will introduce this into this. Right. This is the Prondtl-Meyer equation. So, let us introduce this into this, meaning if I say m1 star, so what I get is m1 and m1 over here, and if this is m2 star, then what I get over here is m2 and m2 over here. So, what I am able to do here is introduce the Mach numbers in regions 1 and 2. So, once I do that, so let me bring that up into here. So, what I get is this, then I rewrite that. So, what I get okay. So, this is the okay. So, like I said, all I did was that if from this equation I brought in m1 and m2, right. So, if you write m1 star, then so basically if you write m1 star, then you get m1, right. So, you introduce this m1 value over here, m1 star value over here, and instead of that, if you need and then you put m2 star, you get m2 here, and you introduce that over here. So, if you do that, then I am just rewriting this equation as m2 and m1. Okay. So, this is a relationship between the two Mach numbers in the two regions. Okay. Okay. So, now that we have done this, what we should be looking at now is the relationship between. So, although we haven't answered the question, right, whether like we said, supersonic flow slowing down to subsonic flow will cause a shock wave or vice versa, right. Now, what we have done here in this equation is that we have written out the Mach number in the region after the shock in terms of the Mach number in terms of the incoming Mach number. Okay. Now, let us try and do that for also the changes in the properties in terms of the density changes, the temperature changes and the pressure changes. Let us do that, okay, and also the entropy change. Okay. Let us do that in terms of the incoming Mach number. Okay. Let us see how those expressions look like, okay, and then we will try to answer the final question. Okay. If I do that, okay, so right. So, I will just write this as right. Now, this is the Prandtl-Meyer expression, right. U1 U2 is equal to A star square. This we have done before, and right. And then what we will write here is basically, so this is nothing but M1 star square, right. Now, M1 star square we can now use from expression which we developed over here, right. This was the M star. So, if you just write that as M1 star, you get this relationship. Okay. So, what we can write over here is, now M1 star square is okay. So, if that is true, then what we can write here is that rho 2 by rho 1. Okay. So, basically, so this is actually equal to rho 2 by rho 1 actually. So, this is okay. So, therefore, this is a relationship between the densities, and that we write in terms of the incoming Mach number, right. This is we write that in terms of incoming Mach number. Now, let us get the expression for pressures and densities. Okay. Now, I am not going to bore you with detailed calculations. Okay. I think by this time you should be able to do this from here. Okay. So, I will just sort of let us say write it out. Okay. Now, if I write this, now P 2 by P 1 is 1 plus 2 gamma by gamma plus 1. Okay, then this is the relationship of the change in pressures with the incoming Mach number. Now, briefly let me just say, just use the momentum equation, the continuity equation, right. So, this is the pressures are here. So, you have the densities here. Now, the densities we have already expressed in terms of the incoming Mach number, and we have the pressures and velocities and densities. Just use these two equations, right, together, and rewrite the values in such a way that you can write it in this form, right, and then introduce the rho 2 by rho 1 into there, and you should be able to get this. Okay, it's just working with those relationships. Okay, and then we need the temperature change. Okay, so I've been able to relate the densities. Okay, then this is the pressure. Let us do it for the temperatures. Okay. So, now we need the temperatures. Now, you can use this. You can use this relationship. Okay. Now, again I am going to just write this out. Now, T 2 by T 1. Okay, T 2 by T 1 is actually right. So, this is it. So, basically we have a relationship for P 2 by P 1 as well as rho 2 by rho 1. So, if we can use these two relationships and get T 2 by T 1, I will still write it out. Okay. So, basically I will write this out, and this comes out to be okay. So, this is what we get. Okay. Now, what is the entropy change? Now, the entropy change is right. If I am not, let me just cross check, right. So, P 2 by P 1, correct. So, then this is the entropy change. Okay. Now, let us look at this and see what. So, T 2 by T 1 is something we have calculated. We have the expression in terms of the incoming Mach number. We also have the relationship for P 2 by P 1 right here for the incoming Mach number. Okay. Now, so now let us try to answer the question which we've been discussing throughout this lecture as to what how exactly should the shock wave be formed? Is it should the incoming Mach number be supersonic or subsonic? Okay. Now, if I have to do that, so let us say, so therefore, let us decide on these three cases in terms of, say, the incoming Mach number is 1. Okay. So, what happens to the entropy change? So, incoming Mach number is 1. So, in that case, what happens to T 2? If you put 1 over here, what you get is 1 from this bracket, and if you put 1 over here, what you get from here is the whole bracket becomes 1. So, basically T 2 by T 1 is 1. Okay. So, T 2 by T 1 is 1. So, which means this term goes to 0, and P 2 by P 1 again is 1, which makes this term also goes to 0. So, which means that S 2 by S 1 is 0. So, if the incoming Mach number is sonic, right, if it is a sonic Mach number is equal to 1. So, there is no entropy change. Okay. So, entropy remains constant, or if I may write it like this, entropy is constant. Okay. Now, let us look at this. If Mach number is, if the incoming Mach number is less than 1, again what I will suggest you is that actually put an actual value into here, into this expression, and see what you get. Okay. So, confirm whatever I am saying over here. So, if Mach number, so let's just say that if Mach number is subsonic, then entropy is decreasing, okay. And if it is supersonic, then entropy is increasing. Again, for these two cases, just take an actual value of this Mach number, so and put it there and see what you get, okay, for the corresponding entropy change. So, in this case, so if Mach number, if it is supersonic flow, then the entropy is increasing. Okay. Now, if that happens, now what do you infer from here? what is your assumption from over here? Now, in all the discussions that we have done so far, right, when we also introduced the characteristic Mach number, we said the changes in all the properties in the flow field are all happening adiabatically, right, which means that this is a physical process in which the entropy cannot decrease. Right. Now, that is so much we know from the second law of thermodynamics. Right. That is why it was important to do a little bit of review of the thermodynamics, because again, as the second law of thermodynamics does, it is giving us the direction in which the physical process should progress, which in here is telling us that it should be at least 0 and increasing, but it cannot decrease, which means that the incoming Mach number for a normal shock wave should always be supersonic. Okay. So, that is so much we are finally able to answer in terms of once we come in terms of the entropy change. Okay. So, therefore, as we have seen, there could be, from the relations that we developed, that mathematically there are more than one possibilities, but if we invoke the conditions for these relationships from the basic laws of thermodynamics, we know that the incoming Mach number has to be supersonic, so that the entropy changes is at least 0 or constant. So, the entropy is at least constant or increasing. Okay. That is so much from thermodynamics. Okay. So, what we have sort of developed today is basically relations of the pressures, temperatures, densities, entropy in terms of the incoming Mach number. Okay. And we have also tried to understand how a shock wave is going to progress. Okay. I mean, it's so the incoming Mach number has to be supersonic, and if that is so, then the Mach number on the other side of the shock wave is subsonic, which we have seen. Okay. So, what we will try to do is develop a couple more relations and look at some typical problems and see if we can understand that. Okay. All right, that should be all. Thank you.